They're lying to you about Mars. Every smiling astronaut, every glossy mission video, every inspirational speech about humanity's future among the stars, all carefully constructed fiction. The first humans who step onto that rust-colored soil are going to die there. And the people sending them know it. And here is a question. If you were the first human to set foot on Mars, what message would you send back to Earth? Let me know in the comments. I will pin the most creative answer. Now let's begin. Mars has captivated our imagination for centuries. We've dreamed of red deserts beneath alien skies, of building cities under protective domes, of becoming a two-planet species. But between our dreams and reality stands a wall of physics so formidable, so unforgiving, that every human who makes that journey might be signing their own farewell letter to Earth. This isn't science fiction fear-mongering. This is the sober assessment emerging from our best scientists, from real data collected by actual missions, from the very engineers designing the spacecraft that will carry the first Martian pioneers. You are made of stardust. Every atom in your body was forged in the heart of a dying star billions of years ago. But those atoms evolved, adapted, and survived within the protective embrace of Earth's magnetic field, beneath a thick atmosphere, under the gentle pull of our planet's gravity. Mars offers none of these protections, and your body, magnificent as it is, wasn't built for the red planet. Let me take you on a journey through the reasons why Mars might become humanity's most distant cemetery. We'll explore the invisible killer that lurks between planets, the betrayal of your own skeleton, the cruel mathematics of fuel and distance, and the psychological gauntlet that breaks even the strongest minds. Each obstacle alone presents a formidable challenge. Together, they form a nearly insurmountable barrier. First, let's talk about something you cannot see, cannot feel, and cannot hide from. Something that's bombarding you right now, even as you watch this video, but in such tiny amounts that your body barely notices. I'm talking about cosmic radiation. When you think of space travel, you might imagine the romance of floating through the cosmos, watching Earth shrink behind you, witnessing the birth of distant nebulae through your spacecraft window. What you probably don't imagine is the invisible storm of particles moving at nearly the speed of light, tearing through your spacecraft's hull, through your spacesuit, through your flesh, and ripping apart the very DNA that makes you who you are. Space is not empty. It's filled with galactic cosmic rays, high-energy particles that have traveled across the universe for millions of years. These aren't just any particles. We're talking about protons, alpha particles, and heavy nuclei moving at velocities that would make your head spin. Some of these particles carry energies measured in billions of electron volts. When they strike matter, including the matter of your body, they don't just pass through harmlessly. They create cascading showers of secondary particles, each one capable of damaging biological tissue. Here on Earth, we're protected. Our planet's magnetic field, generated by the churning of molten iron deep within the core, acts as an invisible shield, deflecting most cosmic radiation away from us. The particles that do make it through then have to contend with our atmosphere, which is thick enough to absorb or scatter the majority of what remains. By the time cosmic rays reach the surface, they've been reduced to a manageable trickle, but in deep space, there is no magnetic field, there is no atmosphere. There is only you, a thin metal shell, and the full fury of the cosmos. NASA's Curiosity rover has been measuring radiation on Mars since 2012. The data it sends back paints a sobering picture. During the 253-day journey from Earth to Mars, astronauts would be exposed to radiation levels approximately 600 times higher than what we experience on Earth's surface. Think about that for a moment. 600 times, that's not a small increase. That's not something you can brush off with better shielding or clever engineering tricks. The ExoMars Trace Gas Orbiter, a joint mission between the European Space Agency and Russia's Roscosmos has been circling Mars since 2016. Its instruments have been meticulously measuring the radiation environment, and the findings confirm our worst fears. A round-trip mission to Mars, lasting roughly 3 years, would expose astronauts to radiation doses that push dangerously close to, and in many scenarios exceed, career limits established by space agencies. The European Space Agency sets a career limit of 1,000 millisieverts for its astronauts. To put that in perspective, a typical chest X-ray gives you about 0.1 millisieverts. A CT scan of your abdomen might be 10 millisieverts. Background radiation on Earth exposes you to roughly 2 to 3 millisieverts per year. Now imagine accumulating doses measured in hundreds of millisieverts during a single journey. Recent research published in the journal Scientific Reports analyzed the radiation exposure during different mission profiles using NASA's latest data. The findings are stark. A traditional 6 to 9 month journey to Mars during solar minimum, when cosmic radiation is at its peak, would result in doses that significantly increase cancer risk, damage to the central nervous system, and potential cardiovascular problems. But here's where it gets even more interesting and perhaps counterintuitive. You might think that traveling during solar maximum, when the sun is most active, and throwing off solar storms and flares would be the most dangerous time. After all, solar particle events can deliver enormous doses of radiation in a matter of hours. Wouldn't it be safer to travel when the sun is quiet? Actually, no. Scientists have discovered a radiation paradox. During solar maximum, the sun's enhanced magnetic field and increased solar wind actually help sweep away galactic cosmic rays, providing a measure of protection. During solar minimum, when solar activity is low, galactic cosmic rays reach their peak intensity, and there's less to deflect them. Research using data from the ExoMars Trace Gas Orbiter confirms that launching during solar maximum could reduce radiation exposure by roughly half compared to a solar minimum mission. Even with this knowledge, even if we time our missions perfectly, the radiation exposure remains severe. Studies estimate that astronauts on a round-trip Mars mission during solar maximum would still accumulate doses between 600 and 700 millisieverts. That's approaching the European Space Agency's career limit in a single mission. During solar minimum, doses could exceed 1,000 millisieverts, pushing well beyond safe thresholds. What does this radiation actually do to your body? The effects are insidious and multifaceted. High-energy particles create ionization tracks as they pass through tissue, breaking chemical bonds and creating free radicals. These free radicals are highly reactive molecules that can damage proteins, lipids, and most critically, DNA. Your cells have repair mechanisms, of course. Evolution has equipped us with molecular machinery capable of fixing damaged DNA. But cosmic radiation overwhelms these systems. When DNA is damaged beyond repair, cells face 3 possible fates. They can die outright, which is actually the least problematic outcome. They can enter a state called senescence, where they stop dividing but continue to secrete inflammatory signals that damage surrounding tissue. Or worst of all, they can survive with mutations that might eventually lead to cancer. The central nervous system is particularly vulnerable. Unlike many tissues in your body, neurons don't regenerate easily. When cosmic rays damage brain cells, the effects can be permanent. Studies on mice exposed to simulated space radiation show concerning results. Impaired memory, reduced cognitive function, increased anxiety, and disrupted decision-making abilities. These aren't trivial concerns when you're piloting a spacecraft or conducting critical repairs millions of kilometers from help. Cardiovascular damage is another serious risk. Radiation can injure the endothelial cells that line blood vessels, promoting inflammation and atherosclerosis. This accelerates the aging of your circulatory system, increasing the risk of heart attacks and strokes years or even decades after exposure. And here's perhaps the most unsettling aspect: we're not entirely sure how bad it will be. Almost all our data on radiation effects comes from studies of atomic bomb survivors, nuclear accident victims, and patients who received radiation therapy. But those exposures were primarily gamma rays and X-rays, which are forms of electromagnetic radiation. Cosmic rays include heavy nuclei particles with far greater mass traveling at relativistic speeds. These heavy ions create dense ionization tracts that cause clustered DNA damage, which is much harder for cells to repair than the diffuse damage caused by gamma rays. Animal studies suggest that heavy ion radiation might be 2 to 3 times more biologically damaging than the same dose of gamma rays, but we simply don't have enough human data to be certain. The astronauts who go to Mars will, in a very real sense, be subjects in an experiment we've never conducted before. Can we shield against this radiation? You might think the solution is obvious: just build thicker spacecraft walls, surround the crew compartment with water or other materials, create a protective cocoon that cosmic rays can't penetrate. Unfortunately, it's not that simple. Traditional shielding materials like aluminum can actually make the problem worse. When high-energy cosmic rays strike aluminum, they create secondary particles through a process called fragmentation. A single incoming cosmic ray, proton, can generate a shower of neutrons, protons, and other particles, some of which can be just as damaging as the original particle. It's like trying to stop a bullet by putting up a target that causes the bullet to explode into shrapnel. Water and hydrogen-rich materials are better. They have lighter nuclei that produce fewer secondary particles. Some spacecraft designs incorporate water tanks in the walls, serving double duty as both radiation shielding and life support reserves. Polyethylene, a type of plastic, has also shown promise. But here's the catch: effective shielding requires mass, and mass is the enemy of space travel. Every kilogram you add to a spacecraft increases the fuel required to launch it, to accelerate it toward Mars, and to slow it down upon arrival. The rocket equation, formulated by Konstantin Tsiolkovsky over a century ago, is unforgiving. Adding significant shielding quickly balloons the mission mass to impractical levels. You end up needing more fuel to carry the shielding, which means more fuel to carry that fuel, in an escalating spiral that can make missions prohibitively expensive or outright impossible with current technology. Some proposed solutions border on science fiction. Magnetic shielding, for instance, would create an artificial magnetosphere around the spacecraft, mimicking Earth's protective field. The concept is sound in principle, but generating a magnetic field strong enough to deflect cosmic rays would require enormous amounts of energy, far beyond what current spacecraft power systems can provide. We're talking about superconducting magnets cooled to near absolute zero, massive power supplies, and complex systems that would need to operate flawlessly for years. The technology exists in laboratories, but deploying it in the harsh environment of space, maintaining it for the duration of a multi-year mission, and ensuring it doesn't fail when you need it most, that's a challenge we haven't solved. Some researchers have proposed using the spacecraft's water supply, sewage, and food stores as shielding, arranging them around a central storm shelter where crew members could retreat during solar particle events. This helps, but only for short-term, acute exposures. Against the constant drizzle of galactic cosmic rays, it provides limited benefit. There are pharmaceutical countermeasures being investigated as well. Antioxidants might help mop up some of the free radicals created by radiation. Drugs that enhance DNA repair mechanisms could potentially reduce mutation rates, but these are still in early research phases, and even optimistic projections suggest they might reduce radiation risk by 20 to 30% at best. That's helpful, but it doesn't eliminate the danger. The harsh truth is that with our current technology, we cannot adequately protect astronauts from cosmic radiation during a Mars mission. We can reduce the exposure somewhat, we can time missions to coincide with solar maximum, We can use better shielding materials, we can develop medical countermeasures, but we cannot eliminate the risk. Every person who travels to Mars will return home, if they return at all, with DNA damage, with an elevated cancer risk, with potential cognitive impairments, with a cardiovascular system that has aged faster than it should have. And remember, this is just the journey there and back. We haven't even talked about what happens to your body during the months or years spent on the Martian surface, where the thin atmosphere provides virtually no protection, and there's no global magnetic field to speak of. We haven't discussed the psychological toll of knowing that invisible particles are bombarding you day after day, that there's nothing you can do about it, that your risk of cancer is climbing with each passing hour. This brings us to an uncomfortable question that space agencies rarely discuss publicly. What is an acceptable level of risk? Here on Earth, we have strict radiation protection standards for nuclear power plant workers, medical professionals, and others who might be occupationally exposed. These standards are based on the principle of ALARA, as low as reasonably achievable. We set limits designed to keep cancer risk below 1% over a lifetime. For Mars astronauts, we're talking about risks that could be 5, 10, or even 20 times higher. We're talking about a 3% increase in fatal cancer risk for every 100 millisieverts of exposure. Do the math on a 1,000 millisievert mission, and you're looking at a 30% increase in lifetime cancer mortality risk. That's on top of whatever your baseline risk already was. Are we willing to send people on missions where there's a substantial chance they'll develop fatal cancer within 10 or 20 years of returning? How do we weigh the scientific and exploratory value against human lives? These are not easy questions, and different space agencies have different answers. NASA's current limits are more conservative than some, but even they acknowledge that Mars missions might require accepting higher risks than ever before. The radiation challenge is formidable, but your body faces another enemy, one that operates more slowly but with equal ruthlessness. This enemy doesn't bombard you from outside, it comes from within, from the very nature of gravity itself, or rather, the lack of it. Let's talk about what happens to your bones and muscles when you leave Earth behind. You weigh less on Mars. That sounds appealing, doesn't it? Imagine stepping onto a scale and finding that your weight has dropped by 62%. If you weigh 70 kilograms on Earth, you'd weigh just 26 kilograms on Mars. You could jump higher, lift heavier objects with ease, move with a spring in your step that would make Olympic athletes jealous. It sounds like a superpower. It's actually a curse. Your skeleton is not a static structure. It's a living, dynamic tissue that constantly remodels itself in response to the forces acting upon it. Every time you walk, run, or simply stand, your bones experience mechanical stress. This stress triggers cells called osteoblasts to build new bone tissue, while other cells called osteoclasts break down old bone. In a healthy adult on Earth, these processes are balanced. You maintain your bone mass, your skeleton stays strong, and you can support your body's weight without your femurs snapping under the load. But remove the weight, remove the stress, and the balance shifts dramatically. In microgravity, or in the reduced gravity of Mars, your bones receive signals that they're overbuilt for the task at hand. Why maintain thick, heavy bones when there's so little force to resist? Your body, in its evolutionary wisdom developed over millions of years on Earth, begins to dismantle your skeleton. Osteoclast activity continues, breaking down bone tissue and releasing calcium into your bloodstream. But osteoblast activity slows to a crawl. The result is a net loss of bone mineral density that occurs at an alarming rate. We know this from decades of studying astronauts on the International Space Station. The ISS orbits Earth at an altitude of roughly 400 kilometers, still within the protective embrace of our planet's magnetic field, but in a state of continuous freefall that creates microgravity. Astronauts living aboard the station for 6 months experience bone loss equivalent to what a postmenopausal woman might lose in a decade. Think about that. 6 months in space equals 10 years of aging for your bones. The areas most affected are the weight-bearing bones, the pelvis, the femur, the spine, the heel. Studies have measured bone mineral density losses of 1 to 2% per month in these regions during spaceflight. A 6-month mission results in roughly 10 to 15% bone loss. Now extrapolate that to a Mars mission. The journey there takes 6 to 9 months. You spend months on the surface, where gravity is only 38% of Earth's. Then comes another 6 to 9 months for the return journey. You're looking at 2 to 3 years of bone loss potentially accumulating to losses of 30, 40, even 50% in critical areas. Research published in the journal PLOS One created mathematical models to predict bone mineral density loss during Mars missions. They analyzed 2 mission profiles, an opposition class trajectory lasting 400 to 600 days and a conjunction class trajectory lasting 1,000 to 1,200 days. The predictions are sobering. For the shorter missions, 62% of crew members would develop osteopenia, a condition defined as significantly reduced bone density that precedes full-blown osteoporosis. 33% would be at risk for osteoporosis itself, where bones become so fragile that minor falls or impacts can cause catastrophic fractures. For the longer missions, the numbers get worse. 100% of crew members would develop osteopenia. The percentage at risk for osteoporosis climbs even higher. These aren't speculative figures. They're based on actual bone loss data from astronauts who have spent extended periods on the ISS, extrapolated using validated mathematical models. Now imagine being on Mars with bones that have lost 40% of their density. You're conducting a geological survey in the Valles Marineris, a canyon system that makes the Grand Canyon look like a ditch. You slip on loose regolith. You fall 3 meters, which on Mars feels like falling just over a meter on Earth. On Earth, you'd probably bruise yourself, maybe sprain something. On Mars, with your compromised skeleton, that fall could shatter your femur, your pelvis could fracture, vertebrae could collapse. There's no hospital on Mars, there's no medevac helicopter, there's no orthopedic surgeon who can pin your bones back together. There's just you, your crew, and whatever medical supplies you brought with you, millions of kilometers from any help. A broken bone that would be a temporary inconvenience on Earth becomes a life-threatening emergency on Mars. But the problems don't end when you return to Earth, assuming you make it back. Your weakened skeleton now has to readjust to Earth's full gravity. The bones that barely supported you in Martian gravity must now bear 2.6 times the load. The risk of fractures during the first weeks and months back on Earth is extraordinarily high. Some astronauts returning from long-duration ISS missions have required wheelchairs, not because their muscles were too weak, though they were, but because their bones couldn't safely bear their weight. Recovery takes time. Studies show that astronauts can eventually regain much of their lost bone density, but not all of it. Even years after returning from a 6-month ISS mission, some astronauts show residual bone loss in critical areas. After a multi-year Mars mission, full recovery might be impossible. You might carry the skeletal damage for the rest of your life at permanently elevated risk for fractures as you age. And we haven't even discussed your muscles yet. Like your bones, your muscles are dynamic tissues that respond to use. Exercise builds muscle, disuse atrophies it. On Earth, you're constantly fighting gravity. Just standing upright requires continuous muscular effort. Your heart is a muscle, and it has to pump blood upward against gravity to reach your brain. Your leg muscles bear your weight. Your core stabilizes your spine. Every movement throughout the day maintains a baseline level of muscle mass and strength. Remove gravity, and those muscles receive a clear message: you're no longer needed. Muscle atrophy in space occurs even faster than bone loss. Studies from the ISS show that astronauts can lose up to 20% of their muscle mass during a 6-month mission, with some muscle groups affected more severely than others. The anti-gravity muscles, those that fight against Earth's pull to keep you upright, atrophy the fastest. Your quadriceps, your calves, your lower back muscles all shrink rapidly. A systematic review published in Sports Medicine analyzed muscle loss during spaceflight and found that even with intensive exercise countermeasures, significant atrophy still occurs. Astronauts on the ISS exercise for about 2 hours every day, using specially designed resistance equipment and treadmills. Despite this rigorous routine, they still lose substantial muscle mass and strength. The exercises help, absolutely, but they cannot fully replicate the constant gravitational loading that muscles experience on Earth. Your heart is particularly vulnerable. It's a muscle that has spent your entire life pumping blood against Earth's gravity. In microgravity or reduced gravity, the heart doesn't need to work as hard. It begins to atrophy like any other muscle. This leads to a condition called cardiovascular deconditioning. Your heart literally shrinks, its walls thin. Its stroke volume, the amount of blood it pumps with each beat, decreases. When you return to Earth's gravity, your weakened heart suddenly has to pump against full gravitational force again. Standing up quickly can cause dizziness or fainting because your heart struggles to maintain blood pressure to your brain. Some returning astronauts experience orthostatic intolerance so severe they cannot stand without assistance for days or even weeks. The Mars 500 experiment, a ground-based simulation where 6 crew members were confined in a mock spacecraft for 520 days to simulate a Mars mission, provided valuable data on muscle changes during long-duration confinement with exercise countermeasures. Even with regular exercise protocols, participants showed significant decreases in muscle strength, particularly in the legs. The results suggest that current exercise countermeasures, while helpful, are insufficient to fully prevent muscle atrophy during multi-year missions. Scientists are exploring more advanced countermeasures. High-intensity interval training shows promise. Resistance exercises using specialized equipment that can generate high forces in limited space might help. Some researchers are investigating pharmacological interventions, drugs that could help preserve muscle mass by blocking the molecular pathways that trigger atrophy. But none of these solutions have been proven effective for missions as long as a Mars trip. There's another insidious aspect to muscle loss: the metabolic consequences. Muscle tissue is metabolically active. It burns calories even at rest. When you lose significant muscle mass, your basal metabolic rate drops. This can lead to unfavorable changes in body composition, with loss of lean mass and potential gain in fat mass, even if total body weight decreases. The shift toward a higher fat-to-muscle ratio has implications for cardiovascular health, insulin sensitivity, and overall metabolic function. Then there's the question of what happens on Mars itself. The surface gravity is 38% of Earth's. That's better than microgravity, certainly. Your muscles and bones will experience some loading, but is it enough? We simply don't know. No human has ever spent extended time in partial gravity. All our data comes from either Earth's 1G or the microgravity of orbit. Mars represents an untested middle ground. Some researchers speculate that Martian gravity might provide sufficient stimulus to slow, though not prevent, bone and muscle loss. Others worry that 38% G is still too little, that astronauts on Mars will continue to atrophy just at a slightly slower rate than in microgravity. Until humans actually spend months on Mars and return to tell the tale, we won't know for certain. What we do know is this: the combination of bone loss and muscle atrophy creates a dangerous positive feedback loop. Weak muscles mean you're less able to perform the exercises needed to maintain bone density. Fragile bones make you more cautious, less willing to exert yourself, which accelerates muscle loss. Add in the fatigue from radiation exposure, the challenges of performing heavy work in a cumbersome spacesuit, and the simple difficulty of maintaining a vigorous exercise routine when you're exhausted and depressed, and the situation becomes even more dire. Consider the practical implications. You've landed on Mars after 9 months of travel. Your bones have lost 15% of their density, your muscles have atrophied by 20%, you're weak, you tire easily, and you're supposed to conduct complex scientific work, maintain your habitat, repair equipment, and explore an alien world. Every task takes longer and requires more effort than it would have on Earth. You're more prone to mistakes, more likely to injure yourself, less capable of responding to emergencies. Now imagine that an emergency does occur. A dust storm damages your solar panels. You need to go outside and perform repairs. The work is physically demanding. You're lifting heavy panels, using tools that fight against you in the thin atmosphere, all while wearing a spacesuit that restricts your movement. Your weakened muscles fatigue quickly. You make a mistake, you drop something, or you lose your balance, or you simply push too hard and feel something give in your lower back. Back on Earth, this would be a manageable situation. On Mars, it could be catastrophic. If you injure yourself badly enough that you cannot continue working, your entire crew is at risk. Mars has no backup team, there's no one else to call. Your crewmates must now handle the workload that was already stretching their own compromised bodies to the limit. The psychological impact of watching your body deteriorate cannot be overstated. Astronauts are selected from among the most physically fit individuals on Earth. They're athletes, pilots, scientists who maintain rigorous fitness standards. To feel yourself growing weaker week by week, to look in the mirror and see muscles that used to ripple now hanging slack, to know that your bones are hollowing out from the inside is profoundly demoralizing. It attacks your sense of self, your confidence, your belief in your ability to handle whatever challenges Mars throws at you. Some proposed solutions to the bone and muscle problem border on the extreme. Artificial gravity through centrifugal force is one option. If your spacecraft or habitat rotates, the centripetal acceleration can simulate gravity. Stand on the inner surface of a rotating cylinder, and you'll feel pressed against the floor as if by gravity. The faster it spins, the stronger the simulated gravity. But there are problems. To create comfortable simulated gravity without inducing nausea from Coriolis forces, you need either a very large diameter or a very slow rotation rate. Most designs call for structures tens or hundreds of meters across. Building such a structure, launching it to space, assembling it in orbit, and maintaining it over a multi-year mission adds enormous complexity and cost. No space agency has yet committed to building a crewed spacecraft with artificial gravity, though concepts have been proposed for decades. Another idea is pharmacological intervention. Drugs called bisphosphonates can slow bone loss by inhibiting osteoclast activity. They're commonly prescribed to osteoporosis patients on Earth. Some astronauts have taken them during space flights with modest success. But bisphosphonates don't build new bone, they only slow the breakdown. And they come with side effects, including potential impacts on kidney function and gastrointestinal issues, neither of which you want to deal with on Mars. For muscle preservation, researchers are investigating myostatin inhibitors. Myostatin is a protein that regulates muscle growth. Block it, and muscles grow larger even without exercise. Sounds perfect, right? Unfortunately, myostatin inhibitors are still experimental, with unknown long-term effects. There are concerns about impacts on other tissues, about the cardiovascular system, about whether artificially boosted muscles would be functionally useful or just cosmetically larger. The reality is that we do not yet have a reliable solution to the bone and muscle loss problem for missions as long as a journey to Mars. We have partial measures, mitigation strategies, ways to reduce the damage, but we cannot prevent it. Every astronaut who goes to Mars will return with a body that has been fundamentally changed, weakened in ways that might never fully heal. And here's something that should give you pause. These effects accumulate. If you go to Mars once and survive, your body might recover enough over several years that you could theoretically go again. But would a second mission compound the damage beyond the point of recovery? Would your bones reach a threshold where even Earth's gravity poses a fracture risk? Would your heart, weakened twice, fail prematurely decades later? We don't have answers because no one has ever done this. The longest any human has spent in continuous microgravity is 437 days, achieved by Russian cosmonaut Valery Polyakov aboard the Mir space station from 1994 to 1995. Polyakov returned safely and recovered, though the process took years. But his mission, long as it was, still falls short of what a Mars journey would demand, and he had the advantage of returning to Earth's full medical care immediately upon landing. Mars astronauts won't have that luxury. After spending months on the Martian surface with weakened bodies, they face another 6 to 9 months of space travel before reaching Earth. By the time they arrive home, if they arrive home, their bones might be so fragile and their muscles so atrophied that simply surviving the landing could be questionable. The forces of atmospheric re-entry and touchdown, normally well within human tolerance, might be enough to cause compression fractures in weakened spines or shatter brittle bones. This raises an uncomfortable question that connects to our title. What if the damage is so severe that astronauts physically cannot make the return journey? What if, by the time the return window opens, their bodies have deteriorated to the point where surviving the trip home is impossible? What if Mars, by virtue of destroying their bodies over months and years, effectively traps them there not through lack of fuel or technology, but through sheer biological breakdown? It's a scenario that space agencies avoid discussing publicly, but privately, in closed meetings and confidential reports, it's a recognized risk. There might come a point in a Mars mission where the crew must make a terrible choice: attempt the return journey with bodies that might not survive it, or remain on Mars indefinitely, accepting that the red planet will be their final home. This isn't hyperbole, this isn't science fiction drama, this is a logical extrapolation from what we know about human physiology and the effects of long-duration spaceflight. We're sending people into an environment that attacks their bodies at a fundamental level, and we're asking them to remain there long enough that the damage might become irreversible. Now let's talk about something that should be straightforward but turns out to be one of the most vexing challenges of the entire endeavor: getting off Mars and coming home. When Apollo 11 landed on the Moon in 1969, Neil Armstrong and Buzz Aldrin descended in a spindly craft that looked like it might fall apart if you sneezed near it. But that fragile-looking lander had something crucial: enough fuel to lift off from the lunar surface and rendezvous with Michael Collins in the command module orbiting above. The Moon's gravity is low, just 1/6 of Earth's. The Moon has no atmosphere to fight against. Escape velocity is a mere 2.4 kilometers per second. The Apollo lunar module's Ascent stage, with its relatively small rocket engine and modest fuel tanks, was more than sufficient for the job. Mars is a different beast entirely. Mars has more than twice the surface gravity of the Moon. Its atmosphere, thin as it is, still creates drag that a spacecraft must overcome. Escape velocity from Mars is 5 kilometers per second, more than double that of the Moon. Getting off Mars requires substantially more energy, which means substantially more fuel, which means substantially more mass, which means you need even more fuel to lift that mass, spiraling into the tyrannical grip of the rocket equation. Here's where the problem becomes almost absurdly difficult. Every kilogram of payload you want to bring back from Mars requires multiple kilograms of propellant. And that propellant has to travel all the way to Mars in the first place, which means you need fuel to carry the fuel, which needs fuel to carry that fuel. The numbers cascade exponentially. Let's run some basic calculations. A crewed Mars Ascent vehicle, something capable of lifting 4 astronauts plus samples off the Martian surface and into orbit, would require approximately 15,000 kilograms of rocket fuel. But that fuel doesn't burn alone. It needs an oxidizer, typically liquid oxygen, to enable combustion. For the type of methane-oxygen propellant systems currently favored for Mars missions, you need roughly 3.5 times as much oxygen as fuel by mass. So those 15,000 kilograms of methane require about 55,000 kilograms of liquid oxygen. That's 70,000 kilograms of propellant you need on Mars to get home, 70 metric tons. Now you could bring all that propellant from Earth. But here's the catch. Launching that mass from Earth, sending it on a trajectory to Mars, and landing it safely on the surface would require a truly staggering amount of fuel. We're talking about multiple heavy-lift launches, complex orbital assembly, and a fuel budget that might require hundreds of metric tons of propellant just to deliver the 70 tons you need on Mars. The economics become prohibitive, the engineering becomes nightmarishly complex, and the risk that something goes wrong multiplies with every additional launch and maneuver. This is why virtually every serious Mars mission architecture includes some form of in situ resource utilization, or ISRO for short. The idea is elegant. Instead of bringing fuel from Earth, make it on Mars using local resources. Mars has what you need. Its atmosphere is 95% carbon dioxide. Its soil contains water ice at many locations, confirmed by multiple missions including NASA's Phoenix lander and the Mars Reconnaissance Orbiter. If you can extract water from the soil and combine it with carbon dioxide from the atmosphere, you can produce methane and oxygen through well-understood chemical processes. NASA's Perseverance rover, which landed in Jezero crater in February of 2021, carries an experiment called MOXIE, the Mars Oxygen In Situ Resource Utilization Experiment. MOXIE is about the size of a car battery, and its job is deceptively simple. It takes in Martian atmosphere, compresses it, heats it to about 800 degrees Celsius, and runs it through a solid oxide electrolyzer that splits carbon dioxide molecules into oxygen and carbon monoxide. The oxygen is collected and measured while the carbon monoxide is vented back into the atmosphere. MOXIE works. It has successfully produced oxygen on Mars multiple times since 2021, demonstrating that the basic chemistry is sound. In one run, it produced about 6 grams of oxygen per hour, enough to sustain an astronaut for roughly 10 minutes. That's a proof of concept, nothing more. But it shows the pathway forward. Scaling up from MOXIE's modest output to the industrial quantities needed for a return mission is where things get complicated. To produce 55,000 kilograms of liquid oxygen, a full-scale ISRU system would need to run continuously for months, possibly years, before the crew even launches from Earth. It would need to process vast quantities of Martian atmosphere. It would require enormous amounts of power, far beyond what solar panels alone could provide unless you deploy solar arrays covering areas the size of football fields. Nuclear power becomes almost mandatory. Then there's the water extraction. Mars does have water ice, but it's not conveniently sitting on the surface in most locations. You have to dig for it, mine it from the soil, heat the regolith to drive off the water vapor, and collect it. This is energy-intensive work requiring robust machinery that can operate in Martian conditions, temperature swings from -125 degrees Celsius at night to a balmy -10 degrees during the day, abrasive dust that gets into everything, and the constant threat of equipment failure with no spare parts store around the corner. Even if you successfully extract water and produce oxygen, you still need to make methane. The Sabatier reaction, known since the 19th century, combines carbon dioxide and hydrogen to produce methane and water. The water can be electrolyzed to produce more hydrogen and oxygen, creating a cycle that theoretically requires only an input of carbon dioxide and energy, but the hydrogen has to come from somewhere initially, and that means either bringing it from Earth or extracting it from Martian water, which takes us back to the mining problem. Research published in Nature Communications explored bioproduction strategies using genetically engineered microorganisms to produce propellants from Martian resources. Photosynthetic cyanobacteria could convert carbon dioxide and sunlight into sugars, which other engineered bacteria could ferment into 2,3-butadiene, a potential rocket fuel. It's a fascinating concept that could reduce power requirements and payload mass compared to purely chemical ISRU. But it's also highly speculative, requiring biological systems to function reliably in the harsh Martian environment, something we've never tested. Let's assume, optimistically, that ISRU works as planned. You land on Mars with a fuel production plant. It runs for 18 months while you conduct your mission, and it successfully generates the 70 tons of propellant you need. Now you face another problem: storing it. Liquid oxygen and liquid methane are cryogenic propellants. Oxygen must be kept below -183 degrees Celsius to remain liquid. Methane must stay below -161 degrees Celsius. On Mars, daytime surface temperatures can reach -10 degrees, which sounds cold but is positively balmy compared to what your propellants need. Keeping 70 tons of cryogenic fuel from boiling away over months requires active cooling systems, heavily insulated tanks, and again, enormous amounts of power. Any boil-off is propellant you've lost, and you can't afford to lose much. A few percent loss might mean the difference between reaching orbit and falling back to the surface. The tanks themselves are a challenge. They need to withstand the internal pressure of the liquids, resist the corrosive properties of the propellants, function through hundreds of thermal cycles as day turns to night turns to day again, and maintain structural integrity even when subjected to Martian dust storms that can last for weeks. These aren't trivial engineering problems. And we still haven't launched. We've just managed to produce and store the fuel. Now you need a rocket capable of using it. The Mars Ascent vehicle needs to be reliable in ways that stretch our current engineering capabilities. It will sit on the Martian surface for months or years, exposed to temperature extremes, dust, ultraviolet radiation, and the slow degradation that affects all machinery. Then, when the time comes, it needs to ignite perfectly on the first try. There are no second chances, there's no ground crew to troubleshoot. If the engine fails to start, if a valve sticks, if a fuel line has developed a leak during the long wait, the crew is stranded. Rocket engines are complex machines with thousands of components, each one a potential failure point. On Earth, before any crewed launch, engines undergo extensive testing, inspection, and maintenance. Teams of engineers pore over every system. Launch can be delayed if anything looks even slightly questionable. On Mars, you don't have teams of engineers. You have whatever automated diagnostics the vehicle carries, the expertise of your crew, and hope. Let's talk about the Ascent itself. You're launching from a planet with a thin but non-negligible atmosphere, in gravity that's lower than Earth's but still substantial, with propellants that have been sitting in tanks for months. The ascent trajectory needs to be precise. Too shallow, and you waste fuel-fighting drag in the upper atmosphere. Too steep, and you expend unnecessary energy fighting gravity. Your guidance systems need to function flawlessly despite months of inactivity. If anything goes wrong during ascent, your options are limited. On Earth, crewed spacecraft have abort modes, escape systems, contingency plans for various failure scenarios. The space shuttle could abort to orbit, abort once around, or abort back to the launch site depending on when the failure occurred. Apollo missions had a launch escape system that could pull the command module away from a failing rocket. On Mars, where do you abort to? If your engine fails halfway through Ascent, you're in a suborbital trajectory with no safe place to land. The surface below is unforgiving. You have no backup rocket. The best-case scenario is a crash landing that your crew might survive if they're extraordinarily lucky. The likely scenario is death on impact. Assuming Ascent succeeds, you're now in Mars orbit, but you're not home yet, not even close. You need to rendezvous with your Earth return vehicle, assuming one is waiting for you in orbit. If you launched from Earth separately, if it made the journey while you were on the surface, it's been sitting in orbit for months, exposed to radiation, micrometeorite impact, and the slow degradation of all space hardware. Does it still work? Will it start when you need it to? The rendezvous itself is a delicate ballet. Your Ascent vehicle has limited fuel reserves. You have a narrow window to match orbits with the return vehicle, approach it carefully, and dock without collision. In Earth orbit, if a rendezvous fails, you can often try again on the next orbit or wait for ground control to calculate a new approach. Around Mars, with communication delays of up to 22 minutes each way, you're on your own. By the time ground control knows you have a problem, it might already be too late to solve it. Once docked, you transfer to the Earth return vehicle, abandoning the Ascent stage in Mars orbit. Now comes the long journey home, which we'll discuss in more detail later. But for now, let's consider what happens if any step of this process fails. If the ISRU system doesn't produce enough fuel, you're stuck. If the propellant boils off faster than anticipated, you're stuck. If the Ascent vehicle malfunctions, you're stuck. If the rendezvous fails, you're stuck. Each of these is not a remote possibility, but a significant risk given the complexity of the systems and the hostile environment they must operate in. Some mission architectures try to mitigate these risks by sending fuel and the Earth return vehicle ahead of the crew. The idea is that you don't launch humans until you've confirmed that their return ride is fueled, tested, and waiting for them. SpaceX's Starship concept, for instance, envisions sending multiple cargo flights to Mars before the first crewed mission, pre-positioning fuel depots, habitats, and supplies. This reduces some risks but introduces others. Hardware sitting on Mars for years before the crew arrives might fail in ways you can't predict or remotely diagnose. There's also the question of redundancy. On a truly safety-focused mission, you'd want backup systems for everything. 2 ISRU plants in case one fails. 2 Ascent vehicles in case one malfunctions, multiple Earth return vehicles, but each additional system multiplies the mission cost and complexity. Space agencies must balance safety against practicality, and that balance inevitably means accepting risks that would be unthinkable for missions closer to home. Let's consider a scenario. You're on Mars. The return window is approaching, the orbital alignment that occurs only once every 26 months, when Earth and Mars are positioned favorably for a relatively low-energy transfer. This is your ride home. Miss it, and you wait another 2 years, assuming your supplies last that long. The ISRU system has produced most of the fuel you need, but not quite all of it. You're 90% fueled. Do you wait and hope the system produces the remaining 10% before the window closes? Do you attempt the ascent with partial fuel, knowing you might not make orbit? Do you skip the return window and gamble that you can survive another 2 years on Mars? None of these choices are good. Each carries risks that could prove fatal, and you have to make the decision with incomplete information, under stress, with your own life and your crewmates' lives hanging in the balance. Now let's add another layer of difficulty: the crew's physical condition. Remember, you've spent months on Mars with bones that are weakening and muscles that are atrophying. The ascent subjects you to multiple Gs of acceleration. On Earth, astronauts train extensively to handle launch forces, and they do so with healthy, fully functioning bodies. You'll be experiencing those forces with a skeleton that has lost significant density and a cardiovascular system that has deconditioned. The acceleration might be enough to cause compression fractures in your spine. The stress on your weakened heart might trigger cardiac arrhythmias. Your blood pressure regulation, already compromised by months in low gravity, might fail completely, causing you to black out during ascent. These aren't theoretical concerns, they're predictable consequences of the physiological changes we know occur during long-duration spaceflight. And if you do black out, if your body can't handle the ascent loads, there's no abort. There's no stopping the rocket and waiting for you to recover. The ascent continues, and you either regain consciousness in orbit or you don't. Your crewmates can't help you. They're experiencing the same forces, dealing with their own compromised bodies. Let's also consider the psychological state of the crew at this point. You've spent possibly 2 years away from Earth. You've endured isolation, confinement, the constant low-level stress of knowing that any equipment failure could kill you. You've watched your body deteriorate. You've probably had conflicts with your crewmates, people you're stuck with in a tin can, with no escape, no privacy, nowhere to go when tensions rise. Now you're about to bet your life on a rocket that's been sitting exposed to Martian conditions for months, fueled by propellants produced by an automated system that has never been tested at this scale before, launching into an ascent profile that has never been attempted with human crew. The level of stress is almost unimaginable. Your judgment might be impaired. Your decision-making abilities, already degraded by radiation exposure, and the cognitive effects of long-term isolation are being pushed to their limits, and yet you need to be sharp, focused, ready to respond to any anomaly during ascent. Some engineers argue that the solution is full automation. Remove the human element from the critical phases. Let computers handle the ascent, the rendezvous, the docking. Computers don't panic. They don't suffer from bone loss or cognitive impairment. They execute their programming flawlessly, assuming that programming is correct and the hardware functions as designed. But computers can't adapt to truly unexpected situations. They can't improvise. They can't draw on intuition or experience to solve problems their designers never anticipated. Apollo 13 survived not because of automation, but because human beings on the ground and in space improvised solutions to a cascade of failures that no one had predicted. On Mars, with communication delays that prevent real-time troubleshooting from Earth, the crew's ability to improvise might be the only thing standing between survival and disaster. This brings us back to the fundamental question. Given all these challenges, given the complexity of producing fuel on Mars, maintaining equipment for years in a hostile environment, launching with compromised bodies from a planet that doesn't want to let you go, is a return journey actually feasible? Let's assume, for the sake of argument, that everything has gone right so far. Your ISRU system worked, you produced the fuel, your ascent vehicle fired perfectly, you made it to orbit, rendezvous with the Earth return vehicle, and now you're pointed toward home. You've escaped Mars. You should be celebrating, right? You've overcome the impossible. Earth is waiting. But between Mars and Earth lies approximately 225 million kilometers of space, give or take, depending on where the planets are in their orbits. And that distance hides dangers that are just as lethal as anything you've faced so far. The journey home takes roughly 6 to 9 months using conventional propulsion and favorable orbital alignments. Some newer mission concepts propose shorter transit times, potentially as low as 3 months, but these require either much more fuel or more advanced propulsion technologies that remain largely theoretical. For now, let's focus on the realistic scenario. You're looking at half a year or more in deep space. You've already spent months on Mars. Your body has been weakened by radiation, reduced gravity, and the general stresses of living in a hostile environment. Now you're transitioning back to microgravity for the return leg. Remember how we discussed bone and muscle loss earlier? It doesn't stop just because you're heading home. If anything, the loss accelerates. After months in Martian gravity, your body had at least some mechanical loading. In microgravity, you have none. The bone loss continues, the muscle atrophy continues, your cardiovascular system continues to decondition. By the time you reach Earth, if you reach Earth, you'll have spent 2 to 3 years away from full gravity. The physiological damage will be cumulative and severe. Studies predict that astronauts returning from Mars missions could have lost 40 to 50% of bone density in critical load-bearing areas. Your muscles could be atrophied to the point where you cannot stand under your own power when you finally experience Earth's gravity again. But let's back up. Let's talk about what happens during those 6 to 9 months of travel through interplanetary space. You're in a spacecraft that's essentially a sealed can hurtling through the void. There's no resupply, there's no turning back. The food you have, the water you have, the oxygen you have, that's all you get. If something breaks, you fix it with whatever spare parts you brought, or you improvise, or you die. Life support systems are extraordinarily complex. You need to scrub carbon dioxide from the air, a process typically done using lithium hydroxide canisters or regenerable systems like the ones on the International Space Station. You need to recycle water from every possible source: urine, sweat, condensation from the air, even the moisture from your breath. The ISS recycles about 93% of its water, an impressive figure, but that means 7% is lost and must be resupplied. On a Mars mission, there is no resupply. Every drop of water lost brings you closer to dehydration. The water recycling systems involve pumps, filters, membranes, sensors, and control electronics. Any of these can fail. A clogged filter might be manageable if you have spares. A failed pump might be repairable if you have the right tools and someone with the expertise, but some failures are catastrophic. If your water recycling system dies completely and you're months from Earth, you'll run out of water long before you get home. Dehydration kills in days. Oxygen generation presents similar challenges. The ISS uses a system called electrolysis that splits water into hydrogen and oxygen. The oxygen is released into the cabin atmosphere. The hydrogen is either vented or combined with carbon dioxide to produce water again, closing the loop. It's elegant in theory, but the hardware is complicated and prone to failures. The ISS has had multiple malfunctions of its oxygen generation system over the years. Each time, the crew had to switch to backup systems or wait for replacement parts to arrive on the next cargo ship. Your Mars return vehicle has no cargo ships coming to save you. Then there's temperature control. Space is not uniformly cold. It's a vacuum, which means there's nothing to conduct heat away from your spacecraft. The only way to shed heat is through radiation. One side of your spacecraft faces the sun and bakes under unfiltered solar radiation. The other side faces the darkness of space and radiates heat away. Without active thermal control, half your spacecraft would be an oven and half would be a freezer. Maintaining a livable temperature throughout requires radiators, heat pumps, fluid loops, and careful management of power systems that generate waste heat. If your thermal control fails, you either cook or freeze, neither of which takes very long. Power generation is critical. Solar panels are the most common choice for spacecraft power, but as you travel back to Earth from Mars, you're starting at a distance where the sun's intensity is only 43% of what it is near Earth. Your solar arrays need to be large to capture enough energy, and they need to remain functional despite months of exposure to radiation and micrometeorite impacts. If power generation drops below critical levels, you have to start making impossible choices. Do you cut life support to conserve power? Do you shut down communications? Do you let the cabin temperature drop to dangerous levels to save electricity? Nuclear power sources avoid the solar distance problem, but they bring their own challenges. Radioisotope thermoelectric generators, like those used on Curiosity and Perseverance rovers, produce power reliably for years, but they generate relatively little electricity, typically measured in hundreds of watts. A crewed spacecraft needs tens of kilowatts. More powerful nuclear reactors are possible, but they're heavy, complex, and present safety concerns. What happens if your reactor fails during the journey? What happens if there's a problem during Earth re-entry? The political and public relations challenges of launching nuclear reactors into space have slowed their development for decades. Let's talk about navigation. You're traveling through space at speeds of tens of thousands of kilometers per hour. To reach Earth, you need to execute trajectory corrections with precision. Fire your thrusters at the wrong time or for the wrong duration, and you could miss Earth entirely. Space is vast. Even an error of a few meters per second in velocity can translate to missing your target by thousands or millions of kilometers after months of travel. Your navigation systems rely on star trackers, accelerometers, gyroscopes, and communication with Earth to determine your position and velocity. But communication delays mean that by the time Earth receives your position data and sends back corrections, minutes or hours have passed. You're largely on your own for real-time navigation decisions. Your onboard computers need to function flawlessly. Your sensors need to remain calibrated. Any drift, any sensor degradation, any computational error, and you could be lost. Now let's consider the human factors. You've spent months, possibly over a year, in close quarters with the same 3 or 4 people. You've been through stressful situations on Mars. You've seen each other at your worst, exhausted, frightened, angry, depressed. You're heading home, which should boost morale, but you're also acutely aware that you're still months away from safety. The finish line is visible, but it's frustratingly distant. Psychological studies of isolated groups show that stress and conflict often peak, not at the beginning or middle of a mission, but toward the end. There's a phenomenon called the third quarter effect, where morale hits its lowest point when you're past the halfway mark, but still far from completion. People become irritable, depressed, and prone to interpersonal conflicts. Small annoyances that you might have tolerated earlier become intolerable. Personality clashes that you manage to smooth over before erupt into serious disputes. In your spacecraft, there's nowhere to go to cool off, no separate room where you can have privacy, no walk around the block to clear your head. You're stuck in a volume roughly the size of a small RV with people you might be starting to hate, and you have months left together. The psychological pressure is immense. Depression is a serious risk. You've left Mars, but you're not yet home. You're in limbo, suspended between worlds. The monotony of the journey wears on you. Days blur together. There's nothing to see out the window except stars that don't appear to move. Earth is still too far away to look like more than a bright dot. Time passes with agonizing slowness. Sleep disturbances are common in space. Without the normal day-night cycle provided by Earth's rotation, your circadian rhythm becomes disrupted. The ISS tries to maintain a 24-hour schedule with programmed lighting changes, but many astronauts still struggle with sleep. On your Mars return vehicle, you might be dealing with insomnia, fragmented sleep, or just poor quality rest that leaves you perpetually exhausted. Chronic sleep deprivation impairs judgment, slows reaction times, and exacerbates depression and anxiety. Some crew members might develop more serious psychological issues. Anxiety disorders, panic attacks, even psychotic episodes are possible, especially given the combination of isolation, stress, physical deterioration, and radiation exposure that affects brain function. If a crew member becomes seriously mentally ill during the return journey, what do? You have limited medical supplies and no psychiatric specialists. Sedation might be an option, but keeping someone sedated for weeks or months creates its own medical complications. And what if someone decides they can't take it anymore? What if someone becomes suicidal? In the confined space of a spacecraft, a single person's mental breakdown can endanger the entire crew. Access to medications, tools, and critical systems would need to be carefully controlled, but implementing security measures in a small crew where everyone needs to trust each other is psychologically corrosive in itself. Let's not forget the radiation exposure continues. You've already accumulated substantial doses during the journey to Mars and your time on the surface. Now you're spending another 6 to 9 months being bombarded by cosmic rays. Every day adds to your cumulative dose, pushing you further past safe limits. The cognitive effects of radiation might already be manifesting: difficulty concentrating, memory problems, impaired decision-making. These effects compound the stress and isolation, creating a vicious cycle. Medical emergencies become especially terrifying during the return journey. What if someone develops appendicitis? On Earth, it's a routine surgery. In space, with no operating room, limited surgical tools, and crew members who might have basic medical training but aren't surgeons, it's potentially fatal. What if someone breaks a bone? Remember, your bones are fragile now. A minor impact could cause a fracture. In microgravity, the bone won't heal properly. It might not heal at all. The injured person becomes a burden on the rest of the crew, requiring care and assistance for the remainder of the journey. Dental emergencies are particularly nasty. A severe toothache, an abscess, a broken tooth, these are more than mere discomfort. They can be agonizing, debilitating, and potentially life-threatening if infection spreads. Your medical kit might include antibiotics and pain medication, but these are temporary measures. Definitive treatment requires a dentist and equipment you don't have. Someone might have to endure weeks or months of dental pain with only basic painkillers for relief. Gastrointestinal issues are another concern. Food on long-duration space missions is limited in variety and not always appealing. Nutritional deficiencies can develop despite careful planning. Vitamin and mineral supplements help, but they're not perfect substitutes for fresh food. Constipation is common in space due to the diet, dehydration, and lack of physical activity. Severe constipation can lead to fecal impaction, which is both excruciatingly painful and potentially dangerous. Now let's talk about trajectory and timing. Your return window from Mars is determined by orbital mechanics. Earth and Mars need to be in the right positions relative to each other to allow a relatively low energy transfer. These windows occur roughly every 26 months. If you miss your window, you wait another 2 years, assuming you have the supplies to last that long, which you almost certainly don't. But here's the problem. The ideal launch window lasts only a few weeks. Launch too early or too late, and you need significantly more fuel to make the journey. Your Earth return vehicle has a finite fuel capacity. If you're forced to launch outside the optimal window due to equipment problems, crew health issues, or any other delays, you might not have enough fuel to reach Earth. You'd end up in an orbit that doesn't intersect Earth's trajectory, drifting through space until your life support fails. Even if you launch during the optimal window, your trajectory must be precise. As you approach Earth, you need to enter a very specific corridor that will carry you into the atmosphere at the right angle. Too steep, and you'll experience crushing deceleration forces that could kill you outright or cause your spacecraft to burn up. Too shallow, and you'll skip off the atmosphere back into space, potentially into an orbit from which you cannot recover. The re-entry corridor for Earth is narrow, typically only a few degrees of angle. Your approach velocity will be approximately 11 kilometers per second, far faster than any spacecraft returning from low Earth orbit. The Apollo command modules re-entering from the Moon hit the atmosphere at about 11 kilometers per second, and that was considered extremely challenging. You're coming in from Mars with similar or even higher velocities, and you're doing it with a weakened body that has spent years away from Earth. The deceleration during re-entry subjects you to multiple Gs of force, potentially as high as 6 or 8 Gs depending on your trajectory and spacecraft design. Remember, your bones have lost 40 to 50% of their density. Your cardiovascular system has deconditioned. The G-forces during re-entry might be enough to fracture your spine, cause your weakened heart to fail, or make you lose consciousness. If you black out during re-entry, you're at the mercy of your spacecraft's automated systems, hoping they function correctly despite years of space exposure. The heat during re-entry is extraordinary. The friction between your spacecraft and the atmosphere at hypersonic velocities creates temperatures that can exceed 1,600 degrees Celsius on the heat shield. Your spacecraft needs an ablative heat shield, material designed to burn away in a controlled manner, carrying heat away from the crew compartment. If there's any damage to the heat shield, any imperfection, any weakness that developed during the years of space exposure, you could burn up during re-entry. There's no way to inspect or repair the heat shield from inside the spacecraft. You commit to re-entry trusting that it will hold, and you find out if you were right in the most unforgiving way possible. Assuming your heat shield holds and you survive the G-forces, you still need to land safely. Parachutes must deploy at the right altitude and inflate correctly. Retro rockets, if your design uses them, need to fire at precisely the right moment. If you're landing on land, the impact needs to be cushioned enough that your fragile bones can withstand it. If you're landing in the ocean, you need to avoid capsizing and wait for recovery ships, while floating in a spacecraft that has limited buoyancy and might be taking on water. The Apollo astronauts returning from the moon were recovered within hours, sometimes minutes, of splashdown. Navy ships were positioned along the re-entry path, ready to retrieve the crew. But will Earth be as prepared for your return? Space agencies plan these things carefully, of course, but you've been gone for 3 years. Budgets change, priorities shift, political support waxes and wanes. What if the recovery forces aren't where they're supposed to be? What if bad weather makes immediate recovery impossible? You could be bobbing in the ocean, unable to exit your spacecraft under your own power, waiting for help that might be hours or days away. And here's something that haunts the edges of mission planning documents, but is rarely discussed openly. What if Earth has decided you're not worth recovering? 3 years is a long time. Public attention is fickle. The initial excitement of the Mars mission might have faded. Budget pressures might have forced cuts to the recovery program. Political changes might have shifted national priorities. You're returning to a planet that might have moved on without you, where you're no longer the heroes who departed, but rather expensive complications that strain budgets and resources. It sounds cynical, perhaps even cruel, but history shows us that support for expensive programs erodes over time. The Apollo program was cancelled after Apollo 17, despite plans for missions through Apollo 20. Skylab, America's first space station, was allowed to fall from orbit and burn up because refurbishing it was deemed too expensive. The Space Shuttle program was retired before adequate replacements were ready. Governments make pragmatic decisions based on current conditions, not past promises. If the political or economic situation on Earth has deteriorated during your absence, if priorities have shifted, if the agency that sent you no longer has the resources or mandate to bring you back, you could find yourself trapped in orbit or stranded after landing, waiting for a recovery that never comes. Let's shift our focus to something that receives less attention than radiation or bone loss, but is equally capable of dooming a Mars mission, the sheer logistical nightmare of keeping humans alive for 3 years in space. You are a biological machine that requires constant inputs and produces constant outputs. Every day, you need approximately 2 kilograms of food, 2 to 3 liters of water for drinking, and roughly 840 grams of oxygen to breathe. You produce about 1 kilogram of solid waste, 1 to 2 liters of urine, and exhale roughly 1 kilogram of carbon dioxide. These numbers might seem small, trivial even, but multiply them by 4 crew members and by roughly 1,000 days for the complete mission, and the scale becomes staggering. A 4-person crew needs approximately 8,000 kilograms of food for a 3-year mission, 8 metric tons. Even with carefully planned, calorie-dense, lightweight rations, that's an enormous mass to transport, and food degrades over time even when carefully packaged and stored. Vitamins break down, flavors deteriorate, textures change. Some foods that are perfectly palatable when fresh become unappetizing or even inedible after months or years in storage. NASA and other space agencies have conducted extensive studies on food shelf life in space conditions. Radiation exposure, temperature fluctuations, and simply the passage of time all degrade food quality. A menu that would sustain your crew for 6 months might become nutritionally inadequate or psychologically unacceptable over 3 years. Imagine eating the same limited selection of freeze-dried, vacuum-packed meals day after day for 1,000 days. The monotony alone is soul-crushing. Nutritional deficiencies are a serious concern. Fresh fruits and vegetables are almost impossible to bring in quantities sufficient for a multi-year mission. They're heavy, perishable, and difficult to store. This means your diet will be lacking in certain nutrients that are difficult to preserve or supplement. Vitamin C degrades relatively quickly. Some B vitamins are unstable over long periods. Fresh food provides thousands of phytochemicals and compounds that we don't fully understand, but that contribute to health in ways that supplements cannot replicate. Some mission concepts include growing food aboard the spacecraft or on Mars. Small hydroponic gardens could theoretically provide fresh vegetables, boost morale, and supplement the stored food supply. The ISS has successfully grown lettuce, radishes, and even chili peppers. But scaling this up to provide meaningful nutrition for a crew over years presents enormous challenges. Plants need light, water, nutrients, and space to grow. They produce oxygen, which is beneficial, but they also respire and can introduce humidity and potential contaminants into the cabin atmosphere. Managing a garden in microgravity or low gravity requires careful attention that your already overburdened crew might not have time to provide. Water is perhaps even more critical than food. You can survive weeks without food, you'll die in days without water. Recycling water to the degree necessary for a Mars mission is technologically challenging. The ISS recycles about 93% of its water, an impressive achievement. But that 7% loss means you need to bring makeup water or face eventual dehydration. For a 3-year mission with 4 crew members, that 7% loss translates to thousands of liters that need to be stored as backup. Water is heavy. Every liter is 1 kilogram. The mass adds up quickly. And water recycling systems are complex and failure-prone. Filters clog, membranes degrade, sensors drift out of calibration, pumps fail. The ISS has experienced numerous water system malfunctions over its decades of operation. Each time, engineers on the ground worked with the crew to diagnose and fix the problem, sometimes sending replacement parts on the next cargo flight. Your Mars mission has no resupply flights. No replacement parts are coming. You have whatever spares you brought, and when those run out, you improvise or you die of thirst. Oxygen generation faces similar issues. Electrolysis systems that split water into hydrogen and oxygen are well-proven technology, but they require power, they require water, and they have components that wear out. The ISS oxygen generation system has failed multiple times and required repairs or replacement parts. Again, on the ISS, this is manageable. On a Mars mission, a catastrophic failure of your oxygen generation system with no way to repair it is a death sentence. You have perhaps days or weeks of reserve oxygen in tanks, and then it's over. Carbon dioxide removal is just as critical as oxygen generation. Humans exhale about 1 kilogram of carbon dioxide per day. In a sealed environment, this quickly accumulates to dangerous levels. Carbon dioxide at concentrations above 1% causes drowsiness and impaired cognition. Above 5%, it causes headaches, dizziness, and shortness of breath. Above 10%, it can cause unconsciousness and death within minutes. Your spacecraft needs systems that continuously scrub carbon dioxide from the air. These systems, whether chemical scrubbers or regenerable systems, all have limitations and failure modes. Temperature and humidity control are vital for survival and sanity. Without proper ventilation, you'd have pockets of hot, humid air mixing with cold, dry air, creating uncomfortable and potentially dangerous conditions. Water condensation on cold surfaces leads to mold growth, which in a sealed spacecraft is a serious health hazard. Mold spores can cause respiratory problems, allergic reactions, and in severe cases, serious infections in immunocompromised individuals. And your immune system, after years in space exposed to radiation and stress, will be compromised. The ISS has dealt with mold and bacterial contamination issues despite having active air filtration and careful monitoring. Some strains of bacteria and fungi have adapted to the space environment, becoming more resistant to countermeasures. Your Mars spacecraft will develop its own microbial ecosystem over the course of the mission, and not all of those microorganisms will be friendly. Keeping the environment clean enough to prevent illness while also not disrupting the beneficial microbiome that you need for digestive health is a delicate balance. Let's talk about waste management, an unglamorous but essential topic. Your body produces waste, and that waste has to go somewhere. On the ISS, solid waste is collected in bags that are eventually loaded onto cargo ships and burned up during re-entry. Urine is processed and recycled into drinking water. This system works for the ISS because waste can be disposed of regularly. On a Mars mission, you don't have that luxury. You could potentially jettison waste into space, but that comes with risks. Every time you open a hatch or dump something overboard, you risk contaminating your spacecraft, losing precious cabin atmosphere, or creating a cloud of debris that could damage your vehicle. Some mission architectures propose storing waste for eventual disposal on Mars or return to Earth, but storing 1,000 days' worth of solid waste from 4 people is both a mass penalty and a potential health hazard. Waste storage areas become breeding grounds for bacteria. They produce odors. They take up space that you might desperately need for other purposes. There's also the question of what to do with waste on Mars itself. You can't just dump it on the surface. Mars is, under international treaties, supposed to be protected from contamination by Earth organisms. Dumping human waste on Mars would violate planetary protection protocols. You need to either sterilize it, bury it deeply, or store it for return to Earth. Each option has challenges and costs. Now let's consider the psychological impact of living in a cluttered, slightly smelly, increasingly degraded environment for 3 years. Humans have a deep psychological need for cleanliness, order, and pleasant surroundings. When your spacecraft starts to look and smell like the inside of a locker room that hasn't been cleaned in months, when equipment starts showing signs of wear and minor malfunctions become normal, when you're surrounded by reminders that everything is slowly falling apart, it grinds down your morale in ways that are hard to articulate but impossible to ignore. Maintenance and repair become constant activities. Every system aboard your spacecraft needs regular upkeep. Filters need changing. Sensors need calibration. Software needs updates. Hardware develops quirks and failures that need troubleshooting. The crew becomes not just explorers and scientists, but janitors, plumbers, electricians, and technicians. The work never ends. There's always something that needs attention, and the list of deferred maintenance grows longer as systems age, and the crew grows more fatigued. The tools and spare parts you have are finite. Early in the mission, when something breaks, you fix it with the proper replacement part. Later, as spares run out, you start improvising. You cannibalize non-essential systems to fix critical ones. You jury-rig solutions using materials never intended for those purposes. The Apollo 13 mission is famous for the improvised carbon dioxide scrubber built from duct tape, plastic bags, and cardboard. The crew survived because engineers on the ground figured out the solution and talked them through it. On Mars, with communication delays, you won't have that real-time support. You'll be on your own, making life or death repairs with whatever you have on hand. 3D printing has been proposed as a solution to the spare parts problem. Bring a printer that can manufacture replacement parts as needed. It's an appealing concept, but current 3D printing technology has significant limitations. You can print simple plastic parts, but you cannot print complex electronics, bearings, seals, or the sophisticated components that make up most spacecraft systems. And 3D printers themselves need maintenance and can fail. You'd need to bring spare parts for your spare parts printer, which somewhat defeats the purpose. Let's talk about communication with Earth. At its closest, Mars is about 54 million kilometers from Earth. At its farthest, it's nearly 400 million kilometers away. Radio signals traveling at the speed of light take between 3 and 22 minutes to make the one-way journey. That means any conversation with mission control has a lag of 6 to 44 minutes between sending a message and receiving a reply. Real-time troubleshooting is impossible. Real-time emotional support is impossible. You're truly on your own. This communication delay has profound implications. On Apollo 13, when the oxygen tank exploded, Mission Control immediately began working on solutions. The dialogue between the crew and ground was continuous and real-time. Decisions were made quickly. Problems were solved through rapid iteration. On a Mars mission, by the time you report a problem and receive advice, 20 minutes or more have passed. If the problem is time-critical, if you need a decision in seconds or minutes, Earth cannot help you. You handle it yourself, or you die. The psychological isolation created by the communication delay is crushing. When you call home to talk to your family, you speak into a microphone knowing that they won't hear your voice for up to 22 minutes, and you won't hear their response for another 22 minutes. Conversations become exchanges of recorded monologues rather than true dialogue. The emotional connection, already strained by the distance and time apart, becomes even more tenuous. You feel the separation in a visceral way every time you try to communicate. And what if something happens to your family while you're gone? What if a parent dies, a child is born, a spouse decides they can't wait 3 years and wants a divorce? You received this news 44 minutes after it was sent, and your response takes another 44 minutes to arrive. You cannot comfort. You cannot participate. You're a ghost haunting the edges of your family's life, aware of events but unable to influence them. The grief, the anger, the sense of helplessness, these emotions eat away at you with no release. Some astronauts might cope by emotionally detaching, by essentially putting their Earth life on hold for the duration of the mission. But humans aren't wired to disconnect so completely. The people you love remain in your thoughts. The life you left behind calls to you. And knowing that life is continuing without you, that you're becoming increasingly irrelevant to the people you care about most, is a special kind of torture. Crew dynamics become increasingly strained as the mission progresses. Psychological research on isolated groups shows predictable patterns. Early in the mission, there's a honeymoon period. Everyone is excited, cooperative, and willing to overlook minor annoyances. As time passes and the novelty wears off, irritations begin to surface. Personality conflicts emerge. Cliques might form, with some crew members growing close while others feel excluded. Leadership challenges arise, resentments build. In a small crew where every member is essential, interpersonal conflicts are catastrophic. You cannot afford to have 2 crew members who refuse to work together. You cannot have someone who undermines the commander's authority. You cannot have feuds, grudges, or the silent treatment. And yet these are all natural human responses to prolonged stress and confinement. Managing these dynamics requires extraordinary emotional intelligence, maturity, and self-control from everyone involved. One person who lacks these qualities can poison the entire crew dynamic. Historical analogues provide cautionary tales. Antarctic research stations, submarines on long deployments, and isolation studies all show that even carefully selected, highly trained individuals can experience severe interpersonal problems during extended confinement. There have been incidents of violence, mental breakdowns, and crew members becoming so dysfunctional that they had to be evacuated. In Antarctica or on a submarine, evacuation is difficult but possible. On a spacecraft between Mars and Earth, there's nowhere to evacuate to. You're stuck with the problem, and it festers. Sexual and romantic relationships add another layer of complexity. If you send mixed-gender crews, the possibility of romantic relationships developing is high. Some of these might be positive, providing emotional support and stability. Others could be disasters, especially if relationships form and then dissolve, leaving ex-partners who still have to live and work together in close quarters. Jealousies, love triangles, and sexual tensions can tear a crew apart. Some have suggested sending all male or all female crews to avoid these issues, but that creates its own problems and doesn't eliminate the possibility of same-sex relationships. There's no perfect solution. Space agencies generally discourage or prohibit romantic relationships during missions, but policies cannot control emotions. People fall in love, they develop attractions. They seek comfort and intimacy in stressful situations. Trying to suppress these natural human behaviors for 3 years is probably futile and might create more problems than it solves. But allowing relationships means accepting the complications they bring. Privacy is almost non-existent on a spacecraft. You're under constant surveillance by cameras, sensors, and your crewmates. There's nowhere you can go to truly be alone. Even the toilet area provides only minimal privacy. This lack of personal space is psychologically oppressive. Humans need solitude, time to process their thoughts without social performance, moments where they don't have to be on. Denying people this for years can lead to serious psychological deterioration. Sleep becomes increasingly difficult as the mission progresses. The combination of stress, irregular schedules, and disrupted circadian rhythms leads to chronic sleep deprivation. You're exhausted all the time, but when you finally lie down to sleep, your mind won't shut off. You think about everything that could go wrong. You replay mistakes. You worry about the future. The sleep you do get is fragmented and unrefreshing. Chronic sleep deprivation impairs judgment, slows reaction times, and exacerbates depression and anxiety. It also weakens your immune system, making you more vulnerable to illness. Now let's confront something that mission planners discuss in closed meetings but rarely acknowledge publicly: the very real possibility that Mars itself will kill you in ways we haven't even discovered yet. We've sent robots to Mars, lots of them. Orbiters, landers, rovers. These machines have taught us an enormous amount about the red planet. We know its atmospheric composition, its surface mineralogy, its temperature ranges, its dust storm patterns. We have high-resolution maps of nearly the entire surface. We've analyzed soil samples, detected organic molecules, and confirmed the presence of water ice. By robotic exploration standards, Mars is one of the most thoroughly studied bodies in the solar system besides Earth. But robots don't breathe, they don't have immune systems, they don't have skin that can absorb chemicals or lungs that can inhale particles. They don't need to eat local resources or drink recycled water that's been processed through Martian soil. The dangers that Mars poses to humans might be entirely different from the hazards that affect our machines, and we won't discover these dangers until humans are actually there, possibly too late to do anything about them. Let's start with the regolith, the loose soil and dust that covers Mars. It's not like Earth soil. It hasn't been weathered by water, processed by life, or softened by organic matter over billions of years. Martian regolith is the product of billions of years of meteorite impacts, volcanic activity, and weathering by wind and extreme temperature changes. The result is a fine, abrasive powder with some extremely unpleasant properties. Martian dust is incredibly fine. Particle sizes are often in the range of 3 micrometers or smaller, far finer than most Earth dust. These particles are also highly angular and jagged, like microscopic shards of glass, because they haven't been worn smooth by wind and water the way Earth particles have been. When you examine Martian dust under an electron microscope, it looks like a collection of tiny knives and needles. This dust gets into everything. The rovers on Mars have struggled with dust accumulation on solar panels, instruments, and mechanical joints. During dust storms, which can envelop the entire planet for months, visibility drops to near zero and the dust becomes absolutely pervasive. It's electrostatically charged, so it clings to surfaces and is difficult to remove. It's also potentially toxic. Analysis of Martian soil by the Phoenix lander and the Curiosity rover has revealed the presence of perchlorates, chlorine-containing compounds that are rare on Earth but appear to be abundant on Mars. Perchlorates are strong oxidizers used in rocket fuel, fireworks, and explosives. They're also toxic to humans. Exposure to perchlorates can interfere with thyroid function, disrupt hormone production, and potentially cause serious health problems with prolonged exposure. The concentrations of perchlorates in Martian soil are significant, typically around 0.5 to 1% by weight. That might not sound like much, but consider that you'll be walking through this soil, working in it, tracking it into your habitat despite your best efforts. Every time you go outside and come back in, you bring Martian dust with you. It gets on your suit, it's in the airlock. Despite cleaning procedures, some inevitably makes it into your living spaces. Over months and years, you and your crew will be exposed to these perchlorates through skin contact, inhalation of dust, and possibly ingestion. We don't fully understand what chronic, low-level perchlorate exposure does to humans over years. Most toxicology studies focus on acute exposure or relatively short-term effects. A 3-year Mars mission represents a duration of exposure that has never been studied. You'd be test subjects in an uncontrolled experiment, discovering the effects firsthand. There's also concern about other potential toxins in Martian soil. Heavy metals, chlorinated and brominated compounds, sulfates, and other chemicals might be present at levels that are harmless to robots but problematic for human biology. We won't know until humans are living there, breathing the dust, touching the soil, and experiencing the cumulative effects over time. Martian dust might also pose a mechanical threat to your lungs. Remember, it's extremely fine and angular. Earth has strict regulations on respirable crystalline silica, a fine dust that can cause silicosis, a progressive and incurable lung disease. Miners, construction workers, and stone cutters who inhale silica dust over years can develop scarred, stiffened lungs that cannot function properly. The angular particles damage lung tissue, trigger chronic inflammation, and lead to fibrosis. There's no cure, the damage is permanent. Martian dust could potentially cause similar or worse damage. It's finer than most silica dust, which means it can penetrate deeper into your lungs. It's more angular, which means it might cause more mechanical damage to tissue, and it might have chemical properties that make it even more inflammatory than silica. Studies conducted on simulated Martian dust using Earth materials that approximate Mars regolith composition have shown that it can be highly toxic to human cells in culture. The dust triggers inflammatory responses, kills cells, and damages DNA. One study published in the journal Icarus exposed human lung cells to simulated Martian regolith. The results were troubling. The dust caused significant cell death and triggered the release of inflammatory molecules. The researchers concluded that inhalation of Martian dust could pose serious health risks. Another study in astrobiology found that Martian regolith simulants were toxic to bacteria, suggesting that the soil chemistry is hostile to life as we know it. Now imagine living on Mars for a year or more. Despite every precaution, despite filtration systems and cleaning protocols, you're inhaling small amounts of this dust regularly. It accumulates in your lungs. Your body tries to clear it, but the particles are so small and so persistent that your immune system can't eliminate them effectively. Chronic inflammation develops, scar tissue begins to form, your lung function gradually declines. You start experiencing shortness of breath, coughing, chest tightness. By the time symptoms become severe, the damage is irreversible. You need to leave Mars immediately, but the return window might be months away. Even if you make it back to Earth, your lungs are permanently scarred, your breathing capacity reduced, your life expectancy shortened. This isn't speculation. This is extrapolation from well-documented effects of fine dust exposure in terrestrial environments. Martian dust, based on everything we know about its properties, could be worse, and you're going to be exposed to it for years. Let's talk about another hazard we've only begun to understand: the potential for toxic chemistry in the Martian atmosphere and on the surface. Mars receives intense ultraviolet radiation due to its thin atmosphere and lack of a protective ozone layer. This UV radiation drives photochemical reactions that create reactive compounds. Hydrogen peroxide has been detected in the Martian atmosphere and likely exists on the surface as well. This isn't the dilute 3% solution you use to clean wounds. This is concentrated reactive hydrogen peroxide that can bleach, corrode, and damage organic materials, including your spacesuit and potentially your body, if exposed. The Phoenix lander in 2008 conducted experiments suggesting that Martian soil, when wetted, might produce even more reactive oxidants. The combination of perchlorates, UV radiation, and the unique chemistry of the Martian environment creates a cocktail of oxidizing compounds that could be highly destructive to organic molecules, including the ones that make up your body. There's a hypothesis, controversial but unsettling, that Martian soil might be essentially sterilizing, so hostile to organic chemistry that life as we know it cannot exist there. This hypothesis emerged from the Viking lander experiments in the 1970s, which produced ambiguous results that could be interpreted as either signs of life or signs of unusual soil chemistry that mimicked biological processes. Subsequent research has leaned toward the chemical explanation. Martian soil is so oxidizing that it destroys organic compounds on contact. If this hypothesis is correct, what does it mean for human habitation? Could the Martian environment damage your equipment faster than expected? Could it react with organic materials in your spacesuit, your seals, your gaskets, causing failures that trap you outside your habitat? Could it contaminate your water recycling systems if Martian soil enters them, creating toxic compounds that you then ingest? These questions don't have answers yet. They're risks we can theorize about but cannot fully assess until humans are on Mars, working with the actual environment under real conditions. And by the time we discover that yes, these are problems, it might be too late to solve them. Now let's consider something even more disturbing: the possibility of unknown microorganisms on Mars. This might sound contradictory given what I just said about Martian soil being potentially sterilizing, but bear with me. Mars might be lifeless now on the surface, scoured clean by radiation and oxidizing chemistry. But what about beneath the surface? What about in protected environments, in caves, in aquifers, in pockets where conditions are less harsh? We know Mars had liquid water on its surface billions of years ago. It had a thicker atmosphere. It might have had conditions suitable for life. If life arose on Mars during that ancient, more hospitable period, could it have survived in subsurface refuges? Could there be Martian microorganisms living beneath the surface, protected from radiation and desiccation, waiting to be discovered? This isn't pure speculation. On Earth, we find life in the most extreme environments imaginable. Microbes live kilometers beneath the surface, in rock pores and aquifers, deriving energy from geological processes rather than sunlight. They survive in Antarctic ice, in acidic hot springs, in the driest deserts. Life on Earth is tenacious and adaptable. If life ever arose on Mars, it might have found ways to persist. Now imagine you drill into the Martian subsurface looking for water ice to feed your ISO system. You break into an aquifer. The water contains microorganisms that have been isolated from the rest of the universe for billions of years, evolving along completely independent pathways from Earth life. You bring that water back to your habitat, you process it, you drink it, you use it to grow food. Those microorganisms enter your body. Your immune system has evolved over billions of years to recognize and fight Earth pathogens. It has no experience with Martian organisms. Their biochemistry might be sufficiently different that your immune system doesn't even recognize them as threats. They might colonize your gut, your lungs, your bloodstream, and your body doesn't mount an effective defense because it doesn't understand what it's dealing with. This is the nightmare scenario of astrobiology, cross-contamination between Earth and Mars leading to disease, death, or ecosystem disruption. The Outer Space Treaty and subsequent planetary protection protocols exist specifically to prevent this. Missions to Mars are supposed to be sterilized to avoid contaminating Mars with Earth life, and return missions, if they bring Martian samples back to Earth, are supposed to quarantine those samples rigorously to prevent Martian organisms from entering Earth's biosphere. But humans are impossible to sterilize. You carry trillions of microorganisms in and on your body. Your gut microbiome alone contains more bacterial cells than you have human cells. When you go to Mars, you bring Earth's biosphere with you. You're a walking contamination event. And when you return, if you return, you bring whatever Martian material you've accumulated with you. Your body, your gear, your spacecraft, all potentially contaminated with Martian dust and possibly Martian microorganisms. Quarantine protocols for returning Mars astronauts would need to be extraordinarily stringent, far beyond what was done for Apollo astronauts returning from the Moon. You might spend weeks or months in isolation upon returning to Earth, monitored for any signs of infection or unusual biological activity. Your samples would be analyzed exhaustively, your gut microbiome would be sequenced and compared to pre-mission baselines looking for foreign organisms. The psychological burden of this after already spending 3 years away from Earth would be immense. And what if signs of Martian contamination are found? What if you're carrying microorganisms that Earth's biosphere has never encountered? The decision-makers would face an impossible choice: release you and risk a potential biological catastrophe, or keep you quarantined indefinitely, perhaps permanently. You might make it back to Earth only to find that you can never truly come home, that you're a biological hazard that must be contained. There's another layer to the contamination problem: contaminating Mars in ways that make it uninhabitable for humans. Imagine you establish a base. Over months and years, Earth microorganisms from your body and your waste inevitably escape into the Martian environment despite your best efforts at containment. Some of these organisms might survive, perhaps even adapt to Martian conditions. They might spread through the regolith, establishing themselves in unexpected niches. Now suppose these Earth microorganisms begin producing metabolic byproducts, competing with ISRU systems, or reacting with Martian soil chemistry in ways that create new hazards. You might inadvertently transform Mars from an environment that, while hostile, is at least understood and predictable into something even more dangerous and unpredictable. You could make Mars less habitable through your very presence. This concept that humans might make Mars worse by going there is rarely discussed in the enthusiastic narratives of Mars colonization. But it's a real possibility grounded in our experience with biological systems. Invasive species on Earth cause ecological catastrophes regularly. Introduce a foreign organism into a new environment, and you often get unpredictable, sometimes disastrous results. Mars would be the ultimate case of introducing organisms into a foreign environment. Let's talk about psychological hazards that are unique to Mars. There's the isolation and confinement we've already discussed, but there's also something more subtle and potentially more disturbing: the alienness of the environment itself. Mars doesn't look like Earth. The sky is butterscotch pink during the day, turning to blue at sunset in a reversal of Earth's colors. The landscape is rust red and barren, devoid of any vegetation, any sign of life, any familiar landmarks. The gravity feels wrong. The sounds are muted because the thin atmosphere doesn't transmit sound the way Earth's does. Everything about Mars screams that you don't belong there. Astronauts on the ISS can look down at Earth, see the blue oceans and green continents, watch weather systems swirl, see city lights at night. That view, while sometimes inducing what's called the overview effect, a profound shift in perspective, also provides a connection to home. Earth is right there, visible and real. On Mars, Earth is just a bright star in the sky, indistinguishable from Venus to the naked eye. You can't see home. You can't see anything familiar. You're surrounded by an alien landscape that offers nothing comforting, nothing that speaks to your evolutionary heritage as a creature of Earth. The psychological impact of this alienation might be more severe than anticipated. There's a concept in environmental psychology called biophilia, the hypothesis that humans have an innate tendency to seek connections with nature and other forms of life. We're drawn to green spaces, water, animals, plants. These connections provide psychological benefits, reducing stress, improving mood, and enhancing overall well-being. Mars offers none of this. It's a dead world. There's no rustling of leaves, no birdsong, no buzz of insects, no life whatsoever.